Hey there, in this video we're going to cover continuity, one-sided limits, and using one-sided limits to determine continuity of a function on a closed interval. So let's pick it up. Continuity, or to be continuous, means what you probably think it means. It means that there is no interruption. And in calculus, a function is continuous at a certain point if it has no interruption at that point. So if we look at f of c, this point over here, the function is said to be continuous at point C because it has no interruption at that point. Okay, so the question I want to answer now is, what do the interruptions or discontinuities look like? And essentially, they can look like one of these three things. So there are three conditions for which the graph of f is not continuous at x equals c. Now, the first one you've seen already. If f of c is not defined, you're going to have either a hole or an asymptote on the graph. So let's cancel that. So that will definitely cause a discontinuity at point C. If the limit of f of x as x approaches c does not exist, that will cause a discontinuity also that can look something like this. And then if the limit of f of x as x approaches c exists, but the limit is not equal to f of c, that should say f of c. Let me fix that a little bit. Put it in one line. So if the limit of f of x as x approaches c exists at x equals c, but is not equal to f of c, that can cause a discontinuity. Let me expand a little bit on that. So there is a limit here at f of c, and that limit is right over here. It would be this value here. This would be the limit at as x approaches c, whatever this value is. So there certainly is a limit of f of x as x approaches c. There certainly is a limit, but that limit is not equal to f of c, because f of c is right over here, this point here. This is your f of c. So that's the third type of discontinuity that you can get. When the limit of f of x as x approaches c is not equal to the value of f of c, that will definitely cause a discontinuity. Okay, so we do have names for discontinuities. The first one we looked at is called a removable discontinuity. The second one we looked at is called a non-removable discontinuity, and the third one is also a removable discontinuity. So what do we get from all this? And then this is the important part. You can say a function is continuous at c if the following three conditions are met. F of c is defined, the limit of f of x as x approaches c exists, and that limit is equal to f of c. So these three conditions have to exist. They have to be met if the function is going to be continuous at point C. So if you go back to that very first function I showed you at the beginning of the video, all those conditions are met here at point C, right? The function is defined at f of c, so it's definitely defined. There's no hole or gap there. There is a limit that exists, and that limit would be over here, right? It would be f of c. So the limit exists and it's equal to f of c. So it definitely meets those three conditions. So for a function to be continuous at point C, these three conditions have to be met. And then I already showed you what it looks like when these conditions are not met in this slide over here. Okay, we're going to continue. Okay, let's talk about the continuity of the functions that we see here. So let me just split this up over here. So let's talk about our first function here, 1 over x. And let's talk about the continuity of it. So I got a graph of it right here. And you can see from the graph that it pretty much looks like it's continuous everywhere, except of course at f of 0. And then, you know, it picks up again after that. So you got you got an asymptote there, right? You have a gap, you have a jump, you have an interruption. And the reason why that is because if you were to plug 0 here for x, you'd have it undefined at x equals 0. So that will definitely cause an interruption. So here's what we can say about the continuity of the function. We can say that it's continuous everywhere, but at x equals 0, it has a removable discontinuity. Okay, let's take a look at our second function that we have here. And our second function is made up of two parts. When x is less than or equal to 0, it's going to take on this function x plus 1. And when x is greater than 0, it's going to take on this function, which is a parabola, x squared plus 1. So our function h of x is made up of these two parts. And you're probably not used to seeing something like that, so let me graph that for you. Let's look at the first part. So it says when x is less than or equal to 0, it's going to take on x plus 1. So basically, everywhere less than 0, you're going to have a line that looks like this, right? And it appears to be defined everywhere up to there. But then when x is greater than 0, it's going to take on x squared plus 1. So let's take a look at that. So it's going to look like this at x greater than 0. So altogether, you have a function that looks like this. Whoops, let me get rid of that. So when x is less than or equal to 0, you have your line, and then when x is greater than 0, you have a parabolic function. So what can we say about the continuity of this function? Well, look, it appears to be continuous everywhere, right? Even at x is equal to 0, it's even continuous here, because remember, when x is less than or equal to 0, it's going to take on x plus 1. So we can say this function is continuous everywhere. Okay, whoops, let me put that back up. Okay, let's keep it moving. Let's talk about one-sided limits. So one-sided limits, we've kind of looked at it, but we're going to now officially look at them. And so again, the way to read this would be the limit of f of x as x approaches c plus, what that means is you're taking the limit from the right. And then the second one, it says the limit of f of x as x approaches c minus, and that would be you're taking the limit from the left. So let's look at an example, and then we're going to talk about why one-sided limits are important. So it says evaluate the limits. So for the first one, we're being asked to evaluate the limit of f of x as x approaches -1 from the right side. So -1 is here, and I'm evaluating the limit as x approaches -1 from the right side. So that would be from this side. So what's the limit? The limit is 2. Now it says, what's the limit of f of x as x approaches -1 from the left side? So here's the left side, so you're approaching it from this side, and the limit is going to be 1. All right, so let's talk about this a little bit, because this is going to bring up a discussion about whether or not the limit as x approaches -1 exists. So the question is, does the limit as x approaches -1 exist? Yes or no? This is important, and make sure you definitely get this. The answer is no, it does not exist, because the limit from the right side does not equal the limit from the left side. Okay, so for a limit to exist at point C, the limit from the left must be the same as the limit from the right as x approaches C. So officially, the limit of f of x as x approaches C from the left side must equal L, and the same thing must happen as you take the limit from the right side. So they both must be the same. They both must be L. Okay, now this is why one-sided limits are important. One-sided limits are important because they help us define continuity on a closed interval. So let me give you the definition first, then we'll work out an example, and then we'll conclude. So definition of continuity on a closed interval. So here's the thing, right? For a function to be continuous on a closed interval, it has to meet three criteria. The function has to be continuous everywhere in the interval. So that's the first criteria. It's got to be continuous here. The second criteria is that you cannot have a gap at A, like a hole or an asymptote, right? This has to be a solid point. And the third criteria is that you cannot have a gap at B. This has to be a solid point. You can't have, a hole, an asymptote, or, a jump or anything like that. That's pretty much the definition in plain language. But let's take a more rigorous mathematical definition. So a function f is continuous on a closed interval when f is continuous everywhere. So that was the first criteria. The second criteria, the limit of f of x as x approaches a from the right side must equal f of a. And that's the second one. And the third one is the limit of f of x as x approaches b from the left side must equal f of b. So that the function f is continuous from the right at a and continuous from the left at b. That's what these two things are saying. Let me break it down. Let me break these two things down for you a little bit more. So what it's saying is, as you take the limit as x approaches a from the right side, you can only take it from the right side, by the way, right? You can't take it from the left side. There's really nothing here. What it's saying is that limit, the limit as x approaches a from the right side has to be equal, it has to be equal to f of a. It's you basically, you can't have like another, you can't have a hole here and then a solid point here like we did with this thing here, right? You can't have this removable discontinuity. That's what it's saying. And let's look at point B, right? The third part. So the limit as x approaches b from the left side must also be equal to f of b. And you can only take the limit here from the left side because there is no right side. So that's what it's saying. That's the definition, right? The definition is of continuity in a closed interval. The functions, it's got to be continuous everywhere inside the interval, and then you can't have jumps at a and b, right? The limit as x approaches a from the right side has to be equal to f of a, and the limit as x approaches b from the left side has to be equal to f of b. Can't have jumps there. Okay, let's work out an example. Is the function below continuous on the interval -1, 1? Okay, first thing, is it continuous everywhere inside the interval? Are there any gaps or jumps inside the interval? No, there are no gaps or jumps inside the interval. It's continuous there. Now what we have to do is we have to take the limit as x approaches a. So here's our a and here's our b. So as x approaches -1 from the right side, so we're going to plug that in to 1 minus x squared. All right, so you plug it in, 1 minus -1 squared, you get 0. So the limit is 0. Now, is that limit equal to f of a, which is f of -1? Well, let's see. Let's plug in for f of -1. So you plug it in, 1 minus -1 squared, you get 0. Yeah, the limit as x approaches -1 from the right side is equal to f of -1. So it's definitely continuous here. It's definitely continuous here. Will it be continuous at b? Well, let's see. So what's the limit as x approaches b, which is 1, from the left side? So let's let me just write that. Plug it in. 1 minus 1 squared equals 0. Is that equal to f of b? Is that equal to f of 1? Yeah, it is. So it's definitely continuous at b. So it's continuous everywhere inside the interval. It's continuous at point A. It's continuous at point B. So what can we say? So here's how I answered the question. Is the function below continuous on the interval -1, 1? Yes, the function is continuous in the provided interval because it's continuous in the closed interval. Moreover, it's continuous at A, so A being -1 from the right, and continuous at B, B being 1 from the left. All right, I really hope this video helps. And just to summarize what we looked at this video, let's go back to our first slide. We defined continuity. We looked at how to take one-sided limits, and then lastly we looked at using one-sided limits to determine continuity of a function on a closed interval. Here's like a nice little summary of the video. You can just read this for yourself and to, I guess, help put things together. All right, take care.